Thanks for joining us today during this unprecedented time. I believe that now, more than ever, time is precious, so let's get cracking. So why does Asset Future exist? We are an asset intelligence company that build or assist in building quantitative and qualitative databases to improve the accuracy of asset data to enhance predictability of building assets. This is in order to facilitate knowledge retention by ensuring lifecycle data continuity from feasibility and planning to design and construct, to operate and maintain, to repurpose or dispose. As you can see, these dotted lines represent the status quo, where there are information silos between the four phases. And we break down these barriers through up-to-date asset registers and, to the best of our ability, predict the future. So why is predicting the future important? Enhancing predictability of building assets is a rising tide that lifts all boats, as it enables line of sight across all stakeholders and empowers evidence-based decision-making. So let's simplify how we predict the future. I'll attempt to break this down into essential parts like a how-to on baking biscuits, for lack of a better example. To predict the future, there are a collection of recipes to follow in terms of data collection and data management, which are significant process flows on their own. And in the interest of time, we will omit those for today. Today, we're going to focus on degradation models. To make a degradation model, we need the essential ingredients of how much, as in how much is it going to cost to maintain, repair, or replace an item, how often, as in how often do we need to maintain or repair an item, and when to action, as in when do we need to replace it. Dynamic degradation estimation is redefining how often and when to action by making specific time points more accurate. So before we dive a bit deeper, let's go through the basic mechanics of an asset future degradation model. So what you're seeing here is a degradation model for a steel framed window in a coastal context where the geographic location is within 1 to 2 kilometers of the nearest ocean or saline body of water. This is what we call a seed model, which serves as a starting point for our new clients when they do not have information on hand in terms of degradation models or depreciation schedules. The graph consists of the asset future condition scale, which ranges from 1 as new to unserviceable as 5. The lifespan of the item on the x-axis, denoted by years, with the dotted line representing the design life of the item. The line graph itself represents the degradation of the item, and the gradient represents the rate of degradation. So the line and the gradient are calibrated annually based upon work orders or time-based information that we receive from each respective client. And we aggregate these calibrations by industry and feed them back into our core model library. In understanding the basic mechanics of a seed model, I'll hand over to Hanbit, one of our lead analysts in terms of dynamic degradation estimation, to go and explore how we've evolved from this point onwards. So I'll hand over to Hanbit.
Yep. Great. Let me just see if everything's working. Can you guys see the slides?
Yep.
Okay, cool. So yeah, thanks, Darren. Hello, everyone. So I'll be presenting about a recent research project we've been conducting in collaboration with the New South Wales Department of Education. The aim of this project was to look at how real-time data from IoT devices can be used to create better degradation models. More specifically, we looked at how motion sensors can be used to infer how much an asset is being utilized, and then use this information to better estimate the degradation of assets. To collect this data, we installed 26 motion sensors across 2 schools in several different locations, such as classrooms, corridors, and other areas. Also, the data was collected between May and December last year. And for our analysis, we excluded the days when students were not at schools, such as public holiday, school holidays, and weekends. Now, the table here shows a clean sample of the data that was collected. As you can see, on average, classroom D had the most students per day compared to the other classrooms. Also, the standard deviations show that the variability in the number of students coming into these classrooms were within a reasonable range. So we can assume that our data is reliable. So many of you may be wondering, what do we do with this data? Or more specifically, how do we incorporate the data into our degradation models? Well, this is done by mathematical modeling, where we use the data to find an accurate measure of asset utilization that takes into account some key parameters. I'll start by breaking this equation down and go through each parameter one by one. So the first part of the equation is relative occupancy rate, which calculates utilization by measuring how many people were using the classrooms compared to what was measured on average. The second part is relative room capacity, which measures how much space was being used given what the recommended room capacity is in accordance with the National Construction Code guidelines. Together, this equation gives us a ratio or a percentage indicating how much an asset is being utilized compared to the average utilization rate for that particular asset type. For instance, if a carpet in a classroom had a duty factor of 2, this would indicate that the carpet was utilized 2 times more than the average amount. In contrast, if the carpet had a duty factor of 0.5, this would indicate that the carpet was utilized 2 times less than the average amount. The weights given to the 2 main parameters of utilization also depends on which industry we are dealing with. For instance, if we are dealing with the education sector, we would give more weight to relative room capacity because measuring how much space students have in a classroom is far more important and better indicator of utilization than the actual numbers of students coming into these classrooms. In contrast, if we are dealing with shopping centers, we would give more weight to relative occupancy rate because shopping centers tend to be built to accommodate for very large capacities, and the number of people coming in will vary significantly day to day. So by calculating asset utilization, we can factor this into our degradation model across different time spans, making it dynamic and more accurate. For instance, when looking at an asset with a 20-year life cycle, the black line here shows the fixed model, which is typically used in our industry. And the orange line shows the dynamic degradation model, which takes into account differences in the utilization rate over time. As you can see, the life cycle of an asset based on a fixed model ends at 20 years, regardless of how much the asset was used. In contrast, the rate of degradation of an asset based on the dynamic model changes according to use over time. For example, because this asset was heavily utilized between its early and mid-life cycle, we see a faster rate of degradation during that period. However, as the asset was utilized much less between its mid to late life cycle, the rate of degradation slows down. Hence why the asset ended with a life cycle of 23 years. Now, when we apply our equation to the data that we collected, we can see which classrooms' assets will degrade faster or slower. For example, here we show that the carpet in classroom B will degrade more slowly as it's being utilized less compared to the carpets in other classrooms. Another advantage of using real-time IoT data, besides making more accurate models, is that it will be possible for decision makers to control the rate of degradation of assets. For instance, the best way to get full use out of the assets in these classrooms would be to try and increase the utilization rate of classroom B. And by doing so, we'll be able to extend the life expectancy of assets in other classrooms. So now that we know how to use IoT data to better estimate degradation, what is our next step? Well, we aim to further fine-tune our equations and test it on a whole range of assets more commonly used in different industries. One broad example of this is that we are currently examining how utilization for some assets will have less impact compared to others, such as external versus internal assets. We are also experimenting with other IoT devices and looking at how their measures could impact assets' life cycles. For instance, one of the measures we are currently looking into is weather and how different weather patterns can affect the rate of degradation. So now as I end our presentation, I'd just like to say thanks to all the people that have contributed towards this project, especially Lily, who worked extensively on developing the equations, and our collaborator, New South Wales Department of Education, for their support and also being with us throughout this journey of learning and development. And for more information about what Asset Future is currently doing or what we are planning on doing in the near future, please visit our website, or you can contact me or Darren via LinkedIn. Cheers.